Hey guys, and welcome back for another sets lesson. I hope you joined us for our previous lesson on set theory and Venn diagrams, as well as the lesson where we talked about set builder notation, which I used down here to define the sets. Because if you're jumping straight in today with sets and probability, you might find it a bit overwhelming. So check out the description box down below where I've linked those previous lessons there for you. Watch those lessons and come back when you're ready. If you've already seen them, let's get started. As well as the basics of set theory and Venn diagrams, I hope you've got the basics of probability down already as well. Probability of any event happening is given as a value between 0 and 1, where 0 is impossible and 1 is certain. Please don't try to convert this into percentages, because the problem is people think that you could have a probability of 52, for example, which is not possible. 52% is the same as the fraction 52 over 100, or the decimal 0.52. But it's generally best, when talking about probability, to keep your answers in fraction form. This is the fraction you should remember about probability. My notation here shows me that the probability that event A happens is the number of ways that A could possibly happen over the total number of possible outcomes. For example, rolling a die. The probability that you roll a 3 on a die is 1 over 6, because there is 1 3 on that die right here, and there are 6 possible values on the die altogether. So 1/6 of your rolls should be a 3. Similarly, flipping a coin, the probability that you flip a heads on a coin is 1 over 2, and that's because there are 2 sides to a coin, and only one of those sides is a head. So half of your flips should turn out to be heads. Your probability for flipping a heads is a half. We could also define probability using set notation, where the probability of event A happening is the number of ways that A could happen over the total number of possible outcomes. Remember this notation here with an N in front of the name of your set? That means the number of elements in that set. And an N in front of this symbol, that's the number of elements in the whole universe and all of the values that we might be considering for a question. Back to our example about rolling a die. Using some set builder notation, I could say that set A are all of the x values where x is a multiple of 3 on a die. So to work out the probability of A is to work out the probability that we roll a multiple of 3 on a die. Having a look at my Venn diagram, I could very simply say that set A is not all of the possible outcomes, it's just the multiples of 3, 3 and 6, while the universe contains all of the possible numbers on a die, 1, 2, 3, 4, 5, 6. So placing those possible values on my Venn diagram, I can see that there are 2 values in set A, and there are 6 values altogether in the universe, but 4 of those values are not inside set A. So the number of elements in A is 2, the number of elements in the universe is 6, so the probability that A occurs, that is the probability that we roll a multiple of 3 on a die, is 2 over 6, or that simplifies to 1/3 by dividing both the numerator and the denominator by a common factor. 2 divided by 2 gives me 1, and 6 divided by 2 gives me 3. Continuing with that same example, suppose I define set B using this set builder notation. B is the set of all y values where y is an even number on a die. So the even numbers on a die, that's 2, 4, and 6. So B contains the values 2, 4, and 6. The number of elements in B are 3, out of the total number of elements in the universe are 6. So the probability of rolling an even number on a die is 3 over 6, or that simplifies to 1/2. Again, we simplify our fraction by dividing both the top and the bottom by our common factor. 3 can divide by 3, that gives 1, and 6 can divide by 3, that gives 2. So there's my simplified probability, left in fraction form. What about P and this symbol you should definitely know from our previous lesson on set theory? That's the intersect. What's the probability that we roll A is a multiple of 3, And the intersect means at the same time it is also an even number on the die. So what's the probability that I roll an even multiple of 3 on the die? Now that's 1/6, because as you can see in my Venn diagram, the only even multiple of 3, here are my multiples of 3, here are my even numbers, is a 6 in the intersection, the intersect of my two sets. So there's one value in the intersect of the two sets. So that's 1 out of the total number of values in the universe, which is 6, 1/6. What about the probability of A, remember this symbol, union B? A union B means the probability that we roll either a multiple of 3 on a die or an even number on the die. The union represents or, either one set or the other, or it could be both at the same time. Looking at my Venn diagram, I can see that A, the multiples of 3 include 3 and 6, and B, the even numbers include 2, 4, and 6. Now I'm going to include all of those possible outcomes because those are the outcomes that are either a multiple of 3 or an even number. But I will only count this 6 once. I won't count it twice. So the probability of rolling an even number or a multiple of 3 is 4 out of 6. 1, 2, 3, 4 values in the union of A and B. Of course, we can simplify this fraction. Both the numerator and denominator can divide by 2. Next, the probability of A union B. We've seen that before, but there's a little line outside. You should remember that means not. This is not the union of A and B. That could also be explained as the probability of not A and not B. So it's not what we just found before, not the union of A and B. Or we could also say that it's not A, but at the same time it's not in B. And that defines just these two values here. This is not a multiple of 3, and nor is it an even number. This is not a multiple of 3, nor is it an even number. The probability of rolling a number which is not a multiple of 3 and it's not an even number is 2 out of 6. Or, of course, we can simplify that. Both the numerator and denominator could divide by 2. That gives us 1/3. Finally, the probability of B intersect not A. That is the probability that it's in set B, so it's an even number, but it's not in A. It's not a multiple of 3. So while it's inside set B, it's not this value here because that value is inside A. So there are two values which are in B but not in A. So the probability of rolling an even number, which is not a multiple of 3, is 2 out of the total number of elements in the universe, which is 6, 2 over 6. And again, we can simplify. Both 2 and 6 can divide by 2. Now that should have been a fairly simple question, but if you need a minute now to hit pause and copy that down, do so before we move on to a slightly more challenging question. This question involves setting up a Venn diagram based on a practical problem and from there working out how many elements there are in each set and subset so that would help us to work out the probability. So reading this question through carefully, I highly recommend that you use highlighters or different colors to point out the different information that's been given, because there's a lot of information here. Don't just look for the numbers because sometimes the numbers are written in words. First of all, the guidance counselor is planning schedules for 30 students. That's how many students there are in total. 16 students say they want to take French. Now 16, watch out, it was not written in numbers, it was written in words, so don't skim over that. 16 students want to take Spanish. 11 students want to take Latin. But be careful because some of these students may want to take more than one of these courses. 5 say they want to take both French and Latin. And 3 of these want to take Spanish as well. So these ones that want to take Spanish want to take all 3 subjects, French, Latin, and Spanish. 5 wanted only Latin, and 8 wanted only Spanish. Let's set out the given information in a slightly clearer way. So let's use some set notation and set out the number of students in each set. First of all, we know that the number of students that we're talking about here, so the number of students in the universe, is 30. We know that 16 of those students want to take French, so I'm calling that set F for French. The number of students who want to take French are 16. Next, we know that 16 want to take Spanish, so I'm going to call that next set S. The number of students in set S are 16. And there are 11 who want to take Latin, so I'll call another set capital L. The number of students who want to take Latin are 11. 5 say they want to take both French and Latin. Remember the symbol that we use for members of more than one set at the same time? That's the intersect. So the intersect of French and Latin should have 5 students in it. So the number of French intersect Latin is 5. And of those, 3 want to take Spanish as well. So these people who want to take Spanish want to take all 3 languages. So that's the intersect of all 3 sets. The number of students in all 3 sets, French intersect Latin intersect Spanish, is 3. 5 wanted only Latin. Now I know we've already said how many students wanted to take Latin. That was 11. But these 5 want to take Latin, but not French and not Spanish. So I need to explain that in my set notation. The number of students who want to take Latin, but not French and not Spanish is 5. And 8 only want to take Spanish. So again, it's not just the number of students taking Spanish, it's the number of students taking Spanish but not French and not Latin. So now that I've set out the different number of students in the different sets and subsets, let's set up our Venn diagram. I've got a rectangle to define the universe, and inside the universe there are these 3 subjects that students are taking. We always start when filling in a Venn diagram with the intersect, because that's the number of students that are in all of these different sets. So we're going to need to exclude that from different parts of the sets. So I'm starting here in the intersect, and these are the students that want to take French, Latin, and Spanish, all 3 at the same time. So the overlap of all 3 sets, and that's 3 students. Next, let's have a look at the number of students who want to take just Latin. So that's not the ones that want to take Latin and French, not the ones that take Latin and Spanish, and not the ones that take all 3 subjects, but just the ones who want to take Latin alone, and that's 5. Next, how many students want to take just Spanish? So that's not the ones that take Spanish and French, not the ones that take Spanish and Latin, just Spanish. So this part of the set S, that's 8. Now we can look at the intersects of these different sets. Here we're told that the number of students who take both French and Latin are 5. So here's French, here's Latin. In between them, this here should be 5. But I already know that of those 5 students, 3 of them also want to take Spanish. So if there's 5 here all together, and 3 is already there, 5 minus the 3, there should be 2 over here. To finish off my Venn diagram, think of how many students are in each of these sets altogether. So the number of students who want to take Latin is 11. And looking at my circle for the number of students who want to take Latin, I can see 5 only want to take Latin. 3 want to take all 3 subjects, and 2 want to take just French and Latin. So that's 5 plus another 5, that's 10 so far. So over here, how many students want to take Latin and Spanish? I wasn't told in my given information. However, I know that this needs to add up to 11. So 11 take away 10. There must be 1 who wants to take both Latin and Spanish. So finishing off my circle of students who want to take Spanish, I know that there are 16 students who want to take Spanish altogether, but 8 of them only want to take Spanish. 1 of them only wants to take Spanish and Latin, and 3 of them want to take all 3 languages. The one missing value that I don't know is how many students want to take just French and Spanish. To work that out, I know that in this full circle, there should be 16 students. And so far I've got 8 9, 12. 16 minus the 12 that I've already got leaves me with 4 students who want to take French and Spanish. Finally, I need to work out the number of students who just want to take French. I know that 3 students want to take all subjects, 4 want to take just French and Spanish, and 2 want to take just French and Latin. So far, that's 4 plus 3, 7, plus 2, 9. And I need 16 altogether, 16 take away 9. There are 7 students who want to take just French. So now that it seems I've completed my Venn diagram, watch out because there's one part of my Venn diagram I did not work out yet. I've worked out the number of students in each of these sets, but what about the number of students who are not in these sets? Are there any students that don't want to take any of these subjects? Let's check to make sure. We know that there are 30 students altogether, and we know how many students there are in each of these sets. So the number of students who do not want to take Spanish, nor French, nor Latin should be 30 minus the number of students we've already listed in those sets. 3 plus 2 plus 1 plus 4 plus 5 plus 8 plus 7. Now that already adds up to 30. So all of my students, there's none left over. All of my students at least want to take one of these subjects. So I can put a 0 out in the rest of my Venn diagram. This is still part of my Venn diagram. It's part of the universe, and I want to be really clear that I haven't forgotten any students. So now on to the actual question here. What is the probability that a student from this group of students wanted to take French only? Looking at my Venn diagram now, here's my set of French students, and I can see that altogether there are 16 students there, but the only students that want to take French only, so none of the other subjects, are these 7 here. So the probability that a student wants to take French only is 7 out of the total number of students in our universe. That's 30. The probability that a student wants to take French, but not Latin and not Spanish, is 7 out of 30. Now that was a slightly more complex example, so please take the time to copy it down, use some different colors to help identify the important information, take care with your Venn diagram, and hit play when you're ready to move on to our practice exercise. Right, so time for some practice now. Go ahead and hit pause so that you can go through this at your own pace. I've given you the Venn diagrams related to the first 2 questions, but the last question you will need to set up that Venn diagram for yourself. Go ahead and hit pause now so you can give that a go, and hit play when you're ready to take it up. I hope you had a chance to hit pause, because here come your answers. For question 1, the probability of a multiple of 3 is 3 out of 10. There are 3 values inside set A, 3, 6, and 9. And altogether, there are 10 values. The universe is the set of integer values between 0 and 10, not including 0, but including 10. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 values in total. P, the probability of A intersect B, is the number of values in the intersect of A and B. That's just this 6 here, so that's 1 value out of the total number of values in the universe. That's 1 over 10. Next, the probability of a number that's not in B. Have a look at how many numbers are not in B. These are the values that are in B, and there are 1, 2, 3, 4, 5 which are not in B. That's 5 out of the total number of values in the universe, which is 10, and 5 out of 10 is equivalent to 1/2. Try to simplify your fractions whenever you can. Next, we're looking at the probability of choosing a value which is in the union of A and B. So it's either a multiple of 3 or it's an even number. And that is 1, 2, 3, 4, 5, 6, 7 values out of a total of 10 values altogether. So the probability is 7 out of 10. Finally, the probability of not being in the intersect of A and B. We already know the number of values in the intersect of A and B, and the probability of choosing a value which is in the intersect of A and B is 1 over 10. So the probability of not choosing a value in the intersect of A and B should be everything else. Remember, total probability adds up to 1 whole. So 1 whole minus the 1/10 should be 9/10. You can also do that by counting. The number of values which are not in the intersect of A and B is 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 10 values altogether. Next, if all of Miss Danielson's students belong to a chorus, band, or orchestra, as shown in the Venn diagram, if one of the students is chosen at random, what is the probability that the student belongs to the chorus but not the orchestra? Now, I stipulated in the question that all of the students belong to at least one of these groups. So I've got no students out here, which would still be part of the question. It's still in my universe of students, but not in these sets. What is the probability that one of my students is chosen at random and that student belongs to the chorus but not to the orchestra? Well, here are my students in the chorus, and there are 10 plus 4 plus 7 plus 5. That's 26 students all together in the chorus. But we don't want to include the students who are in the orchestra, which is the 7 and the 5. So that's just the 10 and the 4. That's 14 students that are in the chorus, but not the orchestra. And the number of students in the whole universe, in the whole question, is 14 plus the 5, 19, plus the 7, 26, plus the 16, 42, plus the 8, 50, plus the 20, 70. There are 70 students all together in my class. Wow, that's a big class. Using set theory notation for that, we could say that the probability of this randomly chosen student being in the chorus, but at the same time they're not in the orchestra, is 14 out of 70. Now I've got 7 out of 35 here. How did I get that? Remember to simplify your fractions as much as possible whenever you can. 14 out of 70 can be simplified by dividing both numerator and denominator by 2. 14 divided by 2 is 7. 70 divided by 2 is 35. Finally, question 3. I hope you took the time to do all your working for this. I'm going to need more space for this. Here's my Venn diagram showing the number of dog owners, cat owners, and fish owners. And reading through the information very carefully, I know that the vet has 26 patrons altogether, so the number in my universe is 26. I know that 14 of these patrons have dogs. I know 10 of these patrons have cats. 5 of the patrons have fish, and 4 patrons have both cats and dogs, both at the same time. That's the intersect. I know that 3 have dogs and fish, so I know the number in the intersect of dogs and fish is 3. 1 has a cat and a fish. If no one has all 3 kinds of pets, the intersect of all 3 is 0. What's the probability of a randomly chosen patron not having any of these types of pets? Let's fill in our Venn diagram. I've already started by filling in the center of my Venn diagram, the intersect of all 3 sets, and we're told that nobody has all 3 pets. So continuing along, starting with the intersects, the number of patrons which have both fish and cats is 1. Now I've got none in here, so this whole region here should have a total of 1. 0 and 1 will make 1. The number of patrons which have dogs and fish, so that's this region here, is 3. And I've got 0 here, so that's not going to take anything away from my total of 3. I'll put 3 there. Next, the number of patrons that have both dogs and cats, that's this region here, is 4. And 4, take away the 0 I've already got here, is still 4. Next, we'll fill in the rest of the sets. So the number of people with fish altogether is 5, but I already know that 1 of them also has a cat and 3 of them also have a dog. So 5 minus the 3 plus 1, that's 4. 5 minus 4, there's 1 person that just has a fish. The number of people who have cats is 10 altogether, but I see in this cat set that I've already got 4 who also have a dog and 1 who also has a fish. That's 5. And 10 minus the 5, that means there's 5 left over here. That's the number of patrons who only have cats. And finally, the dogs. I know that there's 14 people who have dogs altogether, but 4 of those people also have a cat, and 3 of those people also have a fish. 4 and 3, that's 7. The total of 14 minus the 7 I've already got leaves me with 7 who only have dogs. So the probability that a randomly chosen patron doesn't have any types of these pets would be the number of patrons outside of these sets. It's very easy to forget that once you've filled in all of your sets, there's still a possibility that there are some elements in the universe which are not in any of these sets. In set theory notation, this would be the number of non-members of the union of D, C, and F. Because of course the union of all three sets is anybody that's in any of them at all. And we're trying to show the number of values that are outside of that. Now that's going to be the full number of patrons in total in the universe minus the number of patrons we've already placed in their sets. So that's 26 minus the 7, 5, 1, 1, 4, and 3. Altogether, that gives us 21. So 26 minus the 21 that are in these different sets that have these different types of animals is 5. There are 5 patrons that have some other kind of pet. So the probability that we randomly choose a person that doesn't have any of these types of pets, the number of people is 5. Out of the total number of people we're told in the beginning is 26, the probability of somebody not having a dog or a cat or a fish, remember that's our not symbol, is 5 out of 26. So how did you do? I know that we started out quite simple and we got quite difficult, so I hope that you managed. If not, please leave me a comment down in the comment section so I can help you out with any of your doubts. Otherwise, great job, keep it up, and I'll see you soon.